So the first one, this ramp fitting, to give you all a bit of context, I'll give you an introduction to JWST detector readout. In a classical CCD, as a lot of people I think are more familiar with, you wait for the detector well to fill up, and then you dump all that flux out and count it. And you only get one sample at the end of how much flux is in your pixel bins. And you use that to determine the flux in the system. Secondly, you have the JWST detectors, which have a different kind of readout that works up the ramp. So instead of just sampling once at the end, we can non-destructively read the flux in the pixel as we go up the ramp. And then we can get a more precise estimate of the flux of the object by fitting a line to this ramp, these separate data points. So just as a bit of nomenclature, just in case I mentioned it earlier, a group is one read up the ramp. Technically, that's not true, but just for the sake of today, a group is one image up the ramp, and then an integration is an entire ramp itself. So you might think, well, what are the advantages of this? Well, so aside from just being able to fit these different points and getting more precise flux, we also have some advantages in being able to counteract cosmic rays. We can start to detect jumps that happen halfway up the ramp and account for those jumps and get the right flux out for our object. And then also saturation, we can tell roughly when the pixel is saturated, so we can discard that saturated information and still use the ramp before it was saturated. Okay, so as an example of that up the ramp readout, this is JWST exposing on those observations I just showed you, and you can see with every read up the ramp, we get more and more flux on the detector, and you can start to see new information. So you can see the target star in the middle here, and then if you watch this arrow, bang, there's a cosmic ray that's just hit. So the idea is that the pipeline can kind of detect these sorts of cosmic rays and account for them. So there's a ton of stuff that actually happens in what I'm calling the ramp fitting stage, correcting for superbias, correcting for linearity of the detector. I can't touch on all of that today, but spaceKLIP really relies on the JWST pipeline to do a lot of this, to produce these images on the right called these ratings files. So you can see this here. This isn't actually a spaceKLIP reduction. This is sort of when we just turn the JWST pipeline to do things itself. And you can see there's a few different strange artifacts and leftovers in the image. So spaceKLIP gives you the sort of capability to do things slightly differently to kind of avoid some of these artifacts. So you can see these images are the same scaling. And the major thing you'll notice is that the background, that noise just generally in the spaceKLIP image is much higher. And that's actually because we've avoided something called the dark subtraction step. That might seem a bit crazy, but what you'll see is that actually for these early files we're getting, the dark subtraction is doing more harm than good in terms of our data analysis. So to give you a kind of glimpse at these different issues that the default pipeline gives you for now, we have some aggressive saturation correction. You can kind of see these blobs here that if one pixel is detected as saturated, it will mark all boundary pixels as saturated as well. I put a question mark on this one because I do think it's sort of, people have different preferences on this. I know some people are more keen to just say, yeah, let's ignore those pixels. I myself have found that they've been pretty reasonable to use when the saturation isn't like too extreme. The major issue though really is this dark subtraction, residuals, and erroneous jumps. So you can see these kind of black pock marks in the detector. This is from the dark subtraction files, these calibration files. They're not fully put together yet. So what we have is a lot of, cosmic rays. We have a lot of persistence and different hot pixel effects in the dark files themselves. So when we subtract that away from our image, we end up with all these sort of negative subtracted regions, which aren't real astrophysical things. And we get a similar effect from erroneous jumps. So as we're doing this up the ramp readout, sometimes that can get confused. And when you're trying to fit a ramp there, it might think, that some pixel has jumped by some amount of flux when it hasn't really. And that can also confuse the pipeline a little bit and introduce these effects. There are a couple of things that are also in the image that are totally fine. And that's, one, the background sources here. You can see these kind of hexagon shaped things. Those are stars in the image that are just there. That's to be expected. And then also you can see these kind of black squares. These are actually neutral density squares. They're a part of the instrument. And these are used for target acquisition. We position a star behind there to get a good centering before we move it behind a coronagraphic mass. So that's just for NearCam, but I do want to mention quickly as well, there's similar residuals and properties for MIRI. So you can see this is a very, very similar image at the same stage, but for the MIRI coronagraph, and you can see different effects here too, such as this glow stick scattered light. And I'll touch on this later in more detail, but this bright bar of light is certainly not expected. It's not something we thought the instrument would have before launch, so it's something we have to correct for. You have these 4-quadrant phase mask edges, as I mentioned earlier, you have these slight phase offsets, and you can see these edges here in this sort of depressed flux here. And there's also the glow stick scattering kind of happening next to that too. We have reference pixels along the left. These are just these crazy pixels here. Don't worry, they're not used for science, but they are used to sort of calibrate the detector. And then finally, we have the edge of the field of view. This is this like strange drop-off shape here. The field of view is really just this bright region here. You don't need to worry about these sort of strange things happening at the edge. Okay, so I do want to mention one particular issue we had with the MIRI images. So this is after I've subtracted that glow stick on the previous slide. Between two integrations, the first integration and the second integration for the MIRI images, you can see a significantly different level of noise in the images. So integration 1 has these strange sweeping residuals in the image, whereas by integration 2, they're mostly gone, although they do kind of linger a little bit. And the current theory, or as from my understanding, is how this works is basically the dark subtraction files, again, were taken in very quick succession for the calibration program. But for our observation, the telescope has been moving around for a while, and our first observation hasn't really happened. Or our first observation happens after the detector's not been doing anything for a while. So what we get is a lot of built-up charge when the detector tries to reset itself, hasn't fully been sort of drained from the well. So we get this sort of leftover effect, particularly in this first integration. Okay, so a couple of ways to handle some of these issues. The NearCam erroneous jumps, I'll dig into these a little deeper. I mentioned them earlier as kind of these pock marks. What we know is the NearCam coronagraphic subarrays, these images that we take with the coronagraphs, happen in the middle of the NearCam detector. So they're not near any of this reference pixel border that NearCam has. So what that means is, as we're trying to read up the ramp, sometimes the detector can influence the pixels in some way when they're being read out and add or subtract extra flux. And they can kind of, if you look to this top plot here, they can create kind of jumps and wiggles in the up the ramp readout that reduce our ability to accurately measure the flux in each pixel, and can also confuse the pipeline into thinking, that maybe a cosmic ray has happened when it hasn't. So what we're doing with spaceKLIP to kind of account for this is this pseudo-reference pixel correction. We tell the pipeline, we sort of lie to it. We tell it, actually, all these 4 pixels on the border of our image are reference pixels. And it can do a similar routine as it would do for standard reference pixels to address variations that aren't to do with anything astrophysical and are just to do with the detector readout. And you can see here how dramatically that scatter and that variance in our up the ramp readout has changed as a result of doing that. So on the left here, again, I have this pipeline code that's just been running in the background. And what we want to do is we want to just run the ramp fitting. So we're going to say, we're going to set the directory. We're going to tell it what extension of file we want to look for. And then we can set a bunch of different settings similar to the things I mentioned earlier. So we can tweak the saturation boundary and how much that saturation grows to kind of reduce the extent of those broad saturation blobs that I showed earlier. We can tell the pipeline do or do not do dark current subtraction, as well as different steps of the pipeline. Like you can skip this IPC correction or this jump step entirely if you would want. You can tweak the threshold for how significant a deviation the pipeline considers a jump to be. And you can also, here is where you would manually set reference pixels for the image. And then this is just how many cores of your computer do you want to use to do this process. So if I load that in, I can then call the pipeline for this stage just by doing pipeline.rampFit. And that'll start running away. And you can see it's on the right here, created this rampFit directory. And in that directory, we have another directory called sci plus ref. And now it's going to start going through and producing one file at a time. Because this is a little slow. Here we go. We've got one. So I can open this up now. And you can kind of see, okay, we've gone from that image I showed earlier to these ratings images. So now we have an image for each integration for our object, and it's going to go through that for all these different files. So I should have mentioned earlier here what we have here in these different files. We have two files at the bottom. I know they're just numbers, but we have two files for two different roles for the target star, and then everything else is just a reference star observation. So spaceKLIP knows which is which and is going to treat them equally for now, but later on we'll use them in certain ways. So you can see we're just going through all of them now. So like I can open one for the reference star, I can open one for the planet, and you can see they're slightly different, but the shape of the PSF is broadly the same, which is what we want.